Hey everybody, welcome back. So what we're going to do today, in this video, is we're going to look at an application of interference, and that is a device called an interferometer. So an interferometer is a device that utilizes interference of light to measure something, some quantity. And because it's using light interference, it can measure really small things because it's utilizing the wavelength of light in the measurement. And the wavelength of light is very, very, very small. For visible light, again, on the order of, 400 to roughly 780 nanometers, billionths of a meter. Okay, so now there are different types of interferometers depending on the geometry. We're going to look at one called a Michelson interferometer, which is used in some devices. For instance, in our optics lab, we have a wave meter. It's called a wave meter, and it's used to measure the wavelength of a laser. And it uses a Michelson interferometer to do that. But again, there are other interferometers. If you Google them, you'll see, depending on the geometry, where they have the mirrors, how many mirrors, so forth, you have different names for these interferometers. And each has its own sort of special quirks or things it can do better than maybe another geometry, another style of interferometer. But let's talk about the Michelson. So you see that picture right here. And the way it works is the components, you have a light source. So again, often this will be a laser. Okay, so there it is right there. And the light's going to come out of the laser. The next component that's critical is this thing right here. This is called the beam splitter. What does it do? Well, as the name suggests, it splits the beam. The beam splitter is just a piece of glass, and on one side of it, they will have deposited a thin layer of metal. Now, the layer of metal is so thin that not all the light that hits the metal is going to reflect. If they wanted to make a conventional mirror, they would make that layer of metal thick enough so that none of the light would get through. But by varying the thickness of that metal, they can make whatever percentage of the light to reflect that they want, and the remaining percentage will go through. So usually in a Michelson, you use what's called a 50-50 beam splitter, which means that roughly half the light is going to reflect. So let's suppose we follow that. That means it's going to go up this way. The way this mirror is tilted, I should say the beam splitter is tilted, half the light's going to go up, the other half is going to go through. So in this picture, it may be hard to see, but they have an orange ray going up and another orange ray going to the right. Now, what you do, and these two beams now are referred to as the arms of the interferometer. And notice, similar to double slit interference or even the thin film that we talked about, interference, one beam now, right, is split into two. All right, so what you do is, at the end of one arm, you're going to put a mirror, and that's labeled as M1 here, okay? So this beam that goes up is going to hit that mirror. That's going to be 100% reflector, and it's going to come back down. That's that purple ray. Now, when it comes back down, half of that light is going to actually reflect back towards the source. We don't really care about that light. What we're interested in is the remaining light that goes straight through the beam splitter. Okay, so from arm one, you have light ending up going straight down. Now, if you go back to the original beam, when it gets split, look at the path that it travels in arm two. Again, you're going to have a mirror right here labeled M2. So all that light's going to reflect and it's going to come back. Now, half of that's going to go back to the source. We don't care about that. We're interested in the half that reflects because now it's going to be right on top of the light that got transmitted in from arm one. In this picture, don't even worry about this piece of glass, P2. That's known as a compensator, which you don't really need in a basic interferometer if you just want to demonstrate the interference. But some of them will have this compensator plate, And I mean, I'll tell you real quickly what it does is, see in the beam splitter, to get to this metallized part, the light has to go through this thickness of glass right here, right? Well, the compensator compensates for the fact that beam 2, the one that's in arm 2, only has to go through that piece of glass on the beam splitter once, right? So see, the beam that goes up into arm 1, it goes once on its way up and then another time through that glass on its way down. So this compensator makes both beams travel through the glass the same number of times. Again, that's only really important if you're doing really fine work. So like with the wave meter that I was describing, I imagine they have a compensator there because you want to get really high resolution on your measurement. But just to demonstrate the interference pattern, you don't need that. Another thing to ignore is this image of M2. That is there just to help explain the operation of the interferometer. In the textbook that had this picture, just ignore that image of M2. Just forget about it. Okay. The important thing here is that we have two beams, right? One beam going up, down in arm 1, boop, boop, and the other beam going right, left in arm 2. And those meet up again right here, and then those waves are on top of one another. So we can introduce a path difference by moving one of the mirrors, right, in the two arms. So if I move M1 here, right, then I change the total path that arm 1, the light in arm 1 has to travel. So I'm going to get a difference in path between arm 1's path and arm's 2 path. So when they meet up again right here, I could have crest on trough, I'd have no light, or I could have crest on crest and trough on trough, which means I get a bright point. Okay, and depending on the distance that I move the mirror, I can make that point go bright, dark, bright, dark, bright, dark. All right. Now, so one of the things that you can do is you can move this mirror and just count how many bright, dark, bright, dark, bright, dark changes do I see. That's usually called a fringe shift in the jargon of interferometry. And by knowing the number of fringe shifts that you get and knowing the distance that you move that mirror, you can figure out, for instance, the wavelength of the light. That's how the wave meter that we have works. It has a mirror on a little stage on a motor, and it moves that mirror a known amount and counts those bright, dark fringe shifts with an optical detector and can determine the wavelength of the source to a high degree of precision. Another thing that you can do is, if you know the wavelength of the source, you can move the mirror and count those fringe shifts and figure out how far you've moved the mirror. So you might have something that causes a movement, like you might want to look at thermal fluctuations, thermal movement. So you could have this mirror mounted on your object of interest, and as you change the temperature, you could see that mirror moving, and by counting that bright, dark shifting, you could figure out how much motion you had. Another thing that you can do is you could put in here, like let's say in arm 1, don't move the mirrors, but you could put maybe like a block of glass. And because, remember, light changes its wavelength in a material. So by looking at the fringe shifts that you get as you move that block of glass, you can figure out the index of the glass. So you could use the interferometer that way. But I wanted to show you guys a picture. I'm talking about just one point right here, right? Whether that's bright or dark. What you can do, though, is you could put a lens in this laser beam and expand it, make it diverge. So now you have many points of overlap. So you, instead of having, right, just one point of interest, you have many points now that could be bright or dark, depending on the path difference. And if you do that, you'll get this. You saw that picture earlier when I accidentally hit my down arrow. But this is the interferometer, or the interference pattern. Now this is produced with yellow light, and you can see that you get these circular fringes, as they're called, okay? if everything's aligned just perfectly. So pretty neat. And let me see, do I have, oh yeah, I have a video where I built a Michelson interferometer in our optics lab. And you'll see in the video, now my fringes aren't going to be perfect circles because my alignment is not perfect. All these mirrors and the beam splitter and the beam have to be aligned just so, where the beam's perpendicular to all the faces and there's no tilt. So mine aren't perfect circles. But what you'll see in the video is that I'm going to start moving one of the mirrors, and you'll see the so-called fringe shift that I've been describing. It'll look cool because it'll look like these circles are moving in and out. What's really happening is that at all the points on this screen, bright is going to dark and dark's going to bright, but it looks like the circular fringes are moving in and out. Okay, let me show you that video. Okay, here it is right here. I think that'll probably be big enough. So before I play the video, let me just describe here's the laser right here. Okay, this is the lens that's going to diverge the light, spread it out so it's not a real tight beam. This is the beam splitter right here. In the picture that we were looking at, the mirror was up. M1 was up here. Well, here's M1. It's just here. Okay. So instead of being up here, it's down here. And then here's the other mirror, M2. And what I'm going to do is I'm going to turn the lights out. The pattern, the interference pattern is right here on this screen. Sort of hard to see, but we're going to turn the lights out in the video so you'll be able to see the interference fringes better. And this is a red laser. It's a helium neon laser with a red wavelength at about 633 nanometers. And what I'm going to do is I'm going to turn this little knob, and that's going to move this mirror, and you'll see the fringes move. All right, so let's go ahead and play it. And that's just zooming in, showing you the components again. See, that's the beam splitter. It's a circular piece of glass with a thin metal film on it. And here's one of the mirrors right here. Okay. And there are the fringes. Okay, let the camera focus. Again, not perfect circles. And now I'm going to start to move the mirror. Look at that. I'm moving the mirror. Oh, isn't that cool? See, it looks like the fringes are moving inward. And I don't know if I moved it the other way. Let's see if I moved the mirror the other way. Nope, I'm just going the same way. Okay. If I had moved the mirror the other way, you would have seen the fringes moving out. And that is, I don't know who that is right there. Yeah. Okay. That's it. That's what I wanted to show you. Okay, so again, know what an interferometer is, okay? And you should be able to describe the basic parts of a Michelson interferometer and know what you can use them for. Again, you can use them to measure wavelength. You could use them to measure small distances. And when I say small distances, I should point out that if you get a point going from completely bright, as bright as it can be, to dark and then bright again, that is what we would call one fringe shift. That means that you've moved the mirror half of the wavelength of light. So that's amazing, right? So when you saw that video, when you saw a bright circle be replaced with a dark circle and then another bright circle came back to fill that original space, that mirror was being moved half the wavelength of light. That light was about 630 nanometers, so that mirror was moving 315 nanometers, 315 billionths of a meter, or 0.315 microns, millionths of a meter. So again, very small distances can be measured with these interferometers. So again, what can you do with them? You can measure wavelength by moving the mirror a known distance, or you can measure a small distance, knowing the wavelength, and you can also use them to measure indices of refraction, it turns out. That's a little bit more complicated setup, but you can do it. Okay, that's it. See you in the next video where we will talk about holograms. Bye.